Okay, good afternoon, everyone. There's two more topics, two more circuits remaining in op amps that I want to cover today. One is the summing amplifier, the other one is the difference amplifier, and there are also a couple of other fundamental concepts that we need to cover. And so we'll start with the concepts first, then we'll look at summing, and then finally difference amplifier. Sure. Wait, this has not synced yet. Hold on. Okay, so first up is the virtual short and the virtual ground concept. All right, so the op amp, remember the fundamental properties of an ideal op amp is that it has infinite input resistance, it has infinite gain, infinite open loop gain, and zero output resistance, right? So if we have infinite resistance, we model that input resistance as a resistor between the negative and positive terminals. So let me actually just erase this out. And so this input resistance or input impedance of a op amp, internal input resistance. Typical op amp is very high, ideal op amp it's infinite. Now, if it's infinite resistance and we send in any current, is any current flowing through that infinite resistance? No, right? There's no current going in there. So current going in or traveling between these two terminals is zero. If it's zero, that means there is no voltage drop across those terminals. In other words, we are saying that both those terminals are the exact same voltage. Okay. Remember, one of the other properties we discussed was that in the negative feedback configuration, the output is fed back into the negative terminal. And so it's a way of forcing the op amp to have the same voltage at both terminals. So if it's same voltage at both terminals, we say it's virtually a short circuit between the two terminals. And that's where the concept of virtual short comes from. Okay. It's a very useful concept, especially for easing our analyses of any kind of op amp circuits. And so what we do here is they are virtually connected together. That's the concept of the virtual short. And then in the inverting configuration, if the non-inverting terminal is connected to ground, then we can say the inverting terminal is also virtually connected to ground. So we extend the virtual short concept and we say that's the virtual ground concept. Okay, so we extend the virtual short concept and we state that the terminal is virtually grounded. And you will see on the next couple of slides how it eases our analysis. All right. So again, one of the terminals connected to ground, hence the other terminal is also virtually connected to ground. So let's look at this example. We have a circuit with negative feedback. Output is being fed back into the negative terminal. Non-inverting terminal is connected to ground. So from the virtual ground concept, we can state that both the positive and the negative terminals are at ground. Okay. Both terminals are at ground. Non-inverting terminal is physically connected to ground or the reference point, and then the inverting terminal is virtually connected to that same potential. So it does this thing. We have current coming in from our supply right here, input current, and then we have this current coming from the feedback path. Right now, don't worry about what, I'll go over that in just a few minutes, but just think of these two currents coming in and going into the negative terminal. So if you apply KCL at that terminal, so let's say this is the negative or inverting terminal. Right? We have in, and most analyses, what we do is we first apply KCL at the inverting terminal. So you have input current coming in, this current coming in, and this current going out. When that current goes out, it's going into the op amp. Let's call this I in. This is IF, and this would be I minus. I in is the current that's coming from the input that's connected there. Hence I in, IF is the feedback current. So IF and I minus is the current going into the inverting terminal of the op amp. If you apply KCL at this node, what do we get? Two currents coming in, one current leaving. So I in plus IF equals I minus. But because of the high input resistance or infinite input resistance of the op amp, we are saying that this I minus is going to be equal to 0. So what we have here is I in equals minus IF. And by taking that virtual ground concept, we simplify our analysis. Okay. Any input current that is coming from a source or an input that is connected to that op amp is going down the feedback path. Okay. It's not going into the op amp. So we make this assumption and you perform our analysis and then calculate for the voltages and currents. And it greatly simplifies our analysis. So let's take a pause here. Think over that. Let me know if you have any questions. Yes. So the I total, I will go over that in just a minute. It's just that it's specific to that circuit in the feedback loop. For now, let's just assume that it's one single resistor. Does the concept make sense? So far, so good. Okay, then let's answer these questions and look at how we obtain these specific terms. All right, this one is straightforward enough. We have current I in that is going through the 10 kilo ohm resistor because this end is virtually connected to ground. So this is virtual ground right there. Right? It's virtually connected to ground. That both ends of the 10K resistor, we have V in on one end and we have 0 at the other end. So the current I going in is simply V in divided by 10K. Okay, so I in is simply V in divided by 10K. And then here we have the total current coming through here, and it's divided between 3 resistors, 200 kilo ohm resistors and one 10K resistor. The feedback path can be comprised of 1 resistor, 2, 3, 4, 5, 6, 7. However we want to configure it, doesn't really matter, right? So in this case, if we wish to analyze and find the actual current that's coming in, meaning the actual current that is being fed back into the circuit, we can write IF, the feedback path, is the I100K, right? That's this current right here. Now that current is coming from the feedback path from I total. So it's a fraction of I total. If you apply KCL at the top node here between the 3 resistors, you have a certain amount of current going through the 10K resistor. So a fraction of the current goes through there, and a small amount of current goes through this 100 kilo ohm resistor. So on the feedback side, on the output side, we can write I total as the output voltage divided by 100K, which is this resistor in parallel with the 10 kilo ohm resistor. Okay, and the reason we can do this, we can treat it as a series, is because again, there is a virtual ground at the inverting input terminal. That means we have a network that looks like this. This is the first 100 kilo ohm resistor. This is V out right here. This is 100K. This is the other 100K. That one is connected to ground. And then, of course, we have the 10K that is also connected to ground. This right here is the virtual ground at the inverting input terminal. Okay. And that's how it, that's how we obtain this term. Right. So again, total current I that is coming from the output is simply the output voltage divided by the 3 resistors in its pathway. In the 3 resistors, it simplifies the analysis when we apply the concept of virtual ground. And so we can state 100K is in parallel with 10K, is then in series with 100K. And so we have total REQ as 100K plus 100K in parallel with 10K. Let's take a pause. Let me know if you have any questions. Did that make sense? The resistor configuration, right? And of course, once we have I total, once we have the expression for I total, we can then calculate the current for the 100K resistor. Then current for the 100K resistor, we can apply KCL, we can apply current division. And we have I total coming from the top. So this is I total. Let me get this out. This is I TOT coming from the top. And then a portion of it goes down 100K, another portion goes down the 10K. So this is labeled as I100K. And this is not shown, but let's just call it I10K. We apply current division principle, and you can calculate I100K directly from there. Everyone remember current division? Okay. All right, questions? Any questions? Let's just note this down here. Okay, I state current division because it's the easiest way to obtain the answer in one step. Anyway, again, if you had more than 3 resistors in there, you would keep on applying techniques to determine what that final current would be that is entering the inverting terminal. But once we have that, then we can apply this equation that I in plus IF is equal to 0. And that's what we have here. I in is this quantity plus IF is equal to 0. And then we simply plug it in there, and we can directly obtain V out as a function of V in. Okay, so if there was only one resistor in the feedback pathway, we could directly write the answer in like one step. Well, 2 maybe, but it significantly simplifies our analysis. Does everybody see that? That makes sense? Let's take a pause. All right. Okay. All right. So then let's go to a SPICE verification circuit. Again, the results are in front of you right here. So I'm going to say you should build the circuit exactly as shown. And practice it outside of class. Okay. Apply 10 volts power rails plus minus 10 volts, 10 millivolt sine wave peak to peak. Do a transient analysis for 3 milliseconds with 1 microsecond step. And you should be able to obtain this V out. Okay. All right. Summing amplifier. So any questions before I move on to summing? Okay. All right. So these are the two other major configurations for a op amp. One is the summing amplifier. The other one is the difference amplifier. As the name suggests, a summing amplifier is going to sum up all the inputs that we feed into the op amp or connect to the op amp. And a difference amplifier is going to amplify the difference between two signals. Okay. The circuit setup is extremely straightforward. In a summing amplifier, all we do is we take all the other input sources together and we connect them together and feed it into one terminal. If we feed it into the inverting terminal, we have an inverting summing amplifier. If we feed it into the non-inverting terminal, we have a non-inverting summing amplifier. The rest of the configuration remains exactly the way it is. Feedback resistor could be 1 resistor, could be 3, could be 5, 7, 8, 9, 10, could be any configuration we want. But on the input side, all we are doing is we are connecting all the inputs in parallel, we join them together, and then we feed it into one of the terminals. And the output at the op amp is a sum, or it's a weighted sum of all those inputs. And we'll look at in detail how it works and what does weighted sum mean. Does that make sense? Yes, no, kind of. And difference amplifier, you have two terminals, positive, negative, non-inverting and inverting. The output of the op amp is basically the difference between the non-inverting and the inverting amplifier. I mean, inverting input. So it's the non-inverting input minus the inverting input times the closed loop gain of that op amp. So as the name suggests, it amplifies the difference between the two input terminals. And that's it. Those are the two amplifier circuits. Did you all do these kind of circuits in the lab? Summing or in difference? Okay. All right. Okay, so let's take a look. Here we have a, let's say if we don't have this B input, right? We just have VA. What kind of amplifier is this? Where is it connected? Sorry, what? It's an inverting amplifier, absolutely. It's an inverting amplifier, right? We're not doing anything else. Then the only other thing we're doing is we are taking input B and connecting it to that inverting terminal. And that's it. And we have a summing amplifier. The beauty of this is you're just physically taking two inputs, joining them together, and the output is a sum of those input terminals. It can be easily proven by superposition. So if we have linear sources, we have linear resistors, then we can apply superposition. Superposition only applies to linear circuits. So if you apply superposition, voltage source VB is inactive. So VB equals to 0. Only VA is active. Our output is a weighted sum of the input. So minus RF over Rin times the input. So we obtain minus R2 over R1A times VA. So this is will V be inactive? This is VA inactive. So when VA is inactive, the output is a weighted sum of VB, R2 divided by R1B. Superposition at the end, we need to have, let's call this V out 1, actually, V out A and V out B. our actual V out is equal to V out A plus V out B. And so we obtain this expression. Okay. This is a rather straightforward and, dare I say, easy circuit to build. If you're doing an inverting amplifier, or if you're doing non-inverting amplifier for that matter, if you just want to create a summing amplifier, all we do is we take a second input, second input VB, or third input VC, fourth input VD, as many inputs as we want, simply connect it to the inverting terminal or the non-inverting terminal. Okay, and that's, we have a summing amplifier. All right, questions? No questions? All right, cascade of summing amplifiers. We have one right here. And we have the second one. Oh, the pentagon. Okay. So the first one, we have VA and we have VB. What is the discount everything, cover everything up? Just look at this. What is the ratio? On the first 10, absolutely. So for that first stage, we have minus 100K over 10K times VA. How about VB? Let's call it A. What do we have for B? Minus 100K, 20K times VB. Right? That is Vx. So Vx is equal to minus 10 VA minus 5 VB. So what is alpha? Minus 10. What is beta? Minus 5. And then what is gamma? Anyone? I mean, it's right there anyway on the slide. Yeah. Just trying to see who's awake. All right, questions? Where? Let's see. Oh, this one. Final V out. Well, good question. So question being asked is, why is alpha and beta positive in the final V out equation? I'll ask you because you already know the answer. Vx, where is Vx going? Of the second stage. And so what will happen then? That's it. So we had -10 and feeding it back into the inverting terminal. It's a good question. All right. Does everybody see that? Right. All right. Any other questions? Vx or V out? Where? Right here. Because we have an inverting amplifier first stage. Yeah, so it's minus. But then we feed it into another inverting amplifier right here. So then it becomes plus. Yeah. Oh, because that is only going through one amplifier. So VC is simply going to that second inverting amplifier. So it just gets inverted once. Yeah. Okay. All right. Let's look at the difference amplifier. All right. So difference amplifier is a two input circuit. We apply two inputs to both, one each to the inverting and the non-inverting terminal. And then again, the output is a weighted difference of the two inputs. So it's V in plus minus V in minus, okay, or V plus minus V minus. So V out is going to be this, R2 or R1 times V in 1 and R2 or R1 V in 2. V in 2 is the inverting terminal. V in 1 is connected to the non-inverting terminal. Okay. Now the resistors, there is kind of a longish derivation that we usually do for EE students in EE classes, but not so much in here. And once we go through the derivation, we make certain assumptions. One of the assumptions we make is the value of these resistors. Okay, the value of these resistors, meaning the input resistor must have the same values, R1, and then the other resistor must have the same value as the feedback resistor, R2. Okay. Otherwise, the output equation would be different. It would not be the same. Okay, so if R1, R2, and let's just call the other two ones as R3 and R4 were different values, then it would be a very different equation. It wouldn't be as simple and neat as this one. Okay, so here we simply use the same two resistors. We say R2 or R1 times the difference of the two inputs. Okay, so if we look at just this circuit right here, inverting amplifier, we have what? We have a feedback path of R1 and of R2. And so there is a inverting amplifier amplification, so R2 or R1. And then for the V plus terminal, we have R1, 1 plus R2 over R1. Okay. So both circuits, non-inverting as well as inverting amplifier, kind of in one difference amplifier circuit. And we can calculate the V out expression by plugging in V plus into that equation, thus obtain this final expression. Okay. Again, we are not doing any other, in-depth analysis or derivation, but we can use the same virtual ground technique that we used earlier by applying KCL at the inverting terminal, assign currents to all 4 resistors, and then calculating or deriving it from that point on. Okay. This, again, is something students can simulate in LT-SPICE very easily. So I would say, as practice, once you're done with the previous circuit, simulate in LT-SPICE. Okay, simulate in LT-SPICE. That's not something for the exam or anything. That's just for your own learning. Yes. That is correct. Yes. So there would be a virtual short between the two, but not a virtual ground because neither one of the terminals is connected to ground. Yeah. Okay. All right. So to sum up, inverting amplifier configuration, non-inverting amplifier configuration, summing amplifier, difference amplifier. These are the 4 big configurations or the 4 most common configurations for an op-amp. And then there's a 5th one, kind of an important component. You simply take the output terminal and feed it back into the inverting terminal, and you apply input into the non-inverting terminal. This creates a circuit that is known by many names. It's known as the unity gain buffer. It is also known as the voltage follower, also known as an isolation amplifier or isolation buffer. It's the simplest of configurations, but it's a very important circuit in electronics. What it does is we are taking the output and you're feeding it directly back into the input terminal. Because it's negative feedback, the op-amp will try to ensure that both terminals remain at the same level. So when you feed an input into this op-amp, again, there is no, in the feedback path, there is no resistor. In the input side, there is no resistor. The output is exactly the same as the input. Okay. The output is exactly the same as the input. So V out is exactly the same as the input V in. So that begs the question, why is this circuit necessary? What are its applications? And what is its importance? Remember, I said I used the words that this circuit is a very important configuration, and it's used in many electronic circuits, right? So as the name suggests, it's a unity gain amplifier. The gain is 1, hence unity gain amplifier. It's also known as a voltage follower because the output voltage follows the input voltage exactly as it's sent in. Hence the name voltage follower. And then the third is the isolation or the buffer amplifier. And as the name suggests, it provides a buffer between 2 cascading stages of any circuit. Okay. So it is used to isolate 2 cascading circuits. So let's say we have a circuit. The output of that circuit is a certain voltage, right? That is being fed into a second stage. But the current that is coming from the first stage is not sufficient for the second one. So it'll overload it, which in turn would change the output voltage coming from the first stage. Okay. So in order not to have that happen, we insert a isolation amplifier created with an op-amp in the middle. So the input is fed into, or the output from the first stage is fed into the input right here. And then the output of this isolation buffer is fed into the follow-on or the second circuit. And this is from the first circuit going into the second circuit. So it isolates the two because the power to run the op-amp comes from the power rails. So any current that is being supplied by this isolation buffer is coming from the power rails. It's not coming from the first circuit. Okay. The other unique property of this isolation buffer amplifier is that it has very, very high input resistance compared to even non-inverting and inverting term configurations. Okay. There are no resistors in this circuit. It is as simple as taking the output and directly connecting it to the input. This is again another circuit you can easily simulate in LTSpice or on the lab bench. If you have like 10 minutes of time, you could go to the SPL, take your op amps, and connect V in and V out, and automatically see the output results. Okay. So again, the three names for the circuit comes from the fact that the gain is 1. The output voltage follows the input voltage exactly as it's sent in, and it is used to isolate. It's used as a buffer to isolate two cascading stages of any circuit. Okay, yes. So isolation is, let's say you have a, okay, so question being asked is what does isolation mean in this concept context? Isolate simply means, let's say we have a two-stage circuit. Let's say like a preamp going into an amplifier circuit. And the output of the amplifier goes to like speakers, let's say. Then instead of feeding the output of the preamp directly to the amp, we may, of course, this is just a guess on my part. Unity gain isolation buffer amplifier. So the second circuit still receives the same output from the preamplifier, but is now isolated, separated by using that voltage follower circuit. The voltage follower circuit is going to send in the same output that it receives at the input. So the output of the preamp goes into the voltage follower, comes out exactly as it is. However, no current is coming from the preamp. All of that comes from the power rails of that unity isolation gain buffer. Okay, power rails plus VDD and minus VSS. So those are the 5 most important circuits. Inverting configuration, non-inverting configuration, summing, difference, and voltage follower. I know it says 4 right here. The difference is kind of difference amplifier is like not, sorry, not the difference amplifier. Which one is not here? Summing is not in here. Okay, summing is not in here. This is the non-inverting. This is the inverting. This is the difference. And this, of course, is the voltage gain follower. Okay, so that concludes op amps. I'll post a few some practice problems and maybe 1, 2 maybe homework problems, but that's about it. Okay. And on Wednesday, what I'll do is I'll review the entire course just to go over the quizzes and the questions that you can expect in the final exam. Yes. No. So a question being asked is why do we use isolation or why do we need to isolate? To avoid loading effects. So when you have two or more cascaded stages of circuits, um, to avoid the second stage or the following stage from overloading or pulling more current from the preceding stage. So if we place the op amp in the middle, the current to power the op amp comes from the power rails. It doesn't pull it from the first stage of the circuit. So the voltage shape remains exactly the way it is. The voltage level remains the same, but the current changes. So the output current from the first stage is not hindered. And the current for the second stage comes from the op amp. That's what is meant by isolation or isolation buffer. All right, other questions? Any other questions? All right, we'll end class here, and I'll see you all on Wednesday. A form is uploaded for the exam. Your exam is on, let's see. If you have not yet taken a look at the final exam page, you can go ahead and do so. And I'll bring this up again. I mean, I'll go over this on Friday, on Wednesday also. But we are 11501, so exam is on Wednesday, 1:10 to 3 p.m. It's not going to be 1:10 to 3, it's going to be 1:30 to 3:30. So 2 full hours. You have 120 minutes at your disposal. And then the form is here. You submit this form only if you wish to take the exam at an alternative time. Okay. Again, for this section, the exam is on Wednesday from 1 to 4, according to the official Cal Poly schedule. Okay, so there would not be any time conflicts. But if you have another exam before or after, even if you just wish to have more time to study, or if you want to get done early, you can take the exam on Monday, or you can take the exam on Friday, right here in this classroom. Just fill out this form and let me know. Okay. There'll be plenty of space. I'll be able to accommodate more students. If this room gets full, you can open up the room next door, the room opposite, and we should be fine. All right. So I'll read through everything, and then again, we'll discuss this further on Wednesday.